All right, this is a typical problem. It's a rational function, and you look at that. The numerator is the degree of a numerator is larger than smaller than the degree of denominator. But this is a particular case. Okay, the reason is you can simplify first because there's a factor in the denominator. Did you see that? 4x minus 1, 2x. So xx canceled out. You just have this. Okay. Okay, so it's pretty simple now. Okay. So the integral becomes 2 4x minus 1 dx. You don't need to waste time to decompose it to the sum of 2 or 3 functions. Okay. Then use a substitution. If you can write down the answer directly, but make sure you put the correct constant. When you differentiate this, you get denominator, you get 4x minus 1. The numerator, you get 4. But there's only 2 there, so you have to divide by 2. That's it. You can make it quickly. Okay, or you can use a substitution. Okay, but you double check, what constant you put in front of the natural log. Right, when you differentiate 4x minus 1, you get 4. But there's only 2 there. So this is a problem. Okay. The next one is going to be dx x squared plus 1. Okay. I hope you have some ideas to solve this. Right, there's 2 factors in the denominator. One factor is x squared plus 1. It's not a linear factor, right? How do you decompose such functions? Well, x is just x minus 0, right? So you have a over x. But how about x squared plus 1? X squared plus 1 on the top, it should be bx plus c. Bx plus c. Okay. Then after you do the computation, you can quickly determine the coefficients. Here's x squared plus 1, a x squared plus 1 plus b x squared plus cx, right? So you compare both sides. In front of x squared, this should be 0, a plus b 0. Then c is also 0, a is going to be 1. right? You compare this coefficient both sides, right? This is a plus b x squared and plus cx plus a. So this should be equal to 1 compared with the one on the left-hand side. So you can quickly get C0, right? A is 1, so that implies B equals -1. So you will get 1 over x squared plus 1 equals A is 1, B is -1. So it's x over x squared plus 1. And you double check if this is correct, okay? Something can quickly get decomposing without solving the system of linear equations in A, B, C. Okay. So now you find you can evaluate the integral of each of them, right? So it's going to be integral of x and the integral of x over x squared plus 1 dx. So the antiderivative of the first one is absolute x. The second one is if you use a substitution, this will be x squared plus 1. When you differentiate, you get 2x, so you have to divide by 2. So sometimes I skip some steps to use a substitution. I know it's going to be natural of x squared plus 1, but when you differentiate, as a numerator, I get 2x because the derivative of x squared plus 1 is 2x. So I have to divide by 2 in order to get x. Okay. You can also use a substitution, let u to be x squared plus 1 and du equals 2x. Then the integral of x over x squared plus 1 dx is going to be half of du over u. Okay. So you get the same result. Okay. Then you replace u by x squared. Okay. So this is a kind of decomposition, and okay, so that's all about the review on those problems. Today we're going to focus on section 7.7. Now, what is section 7.7 about? This is about integral. Well, we learned integrals, right? This is not 166. Okay, we're trying to understand. Yeah, this is a definite integral. Okay, the meaning of the how to define the definite integral. Yeah, this is a f of x dx. Okay. By definition, yes.
On the last one, how was the last part? Up with 1/2 u the same as how do you get
From here to here?
Yeah.
Oh, you see, I use substitution, let u to be x squared plus 1. So I get 1/2 of this, then this will be a net half of the natural log of u. But then you have to replace u by x squared plus 1 because x squared plus 1 is always positive. You don't need to put up a silver symbol. So that's why this is how do you get, right? Yeah.
So what? Oh, there was only half of the problem.
Yeah, half of the problem. I already get this part. The question, how can I get this, right? First of all, by guess and try. I did not even go through this step. I just said that you see you have x squared plus 1, and you know you're going to use substitution, but you did not actually use it. You should be just try natural log of x squared plus 1. But when you differentiate, you get 2x on the top. So there's only one x there. That's why you divide by 2. Okay, then you save your time. Okay, but if you really have to use substitution, this is the way how to do that. Okay, so the point is, as long as you get the right antiderivative of the function, it doesn't matter which way you get. Okay, even you memorize the answers, then just put that. But double check that this is correct antiderivative of the function. Okay, just differentiate. Okay. So we have studied this indefinite integrals, even definite integrals, and here today we're going to learn how to estimate the definite integral. So to do that, we needed to know what's the definition of a definite integral. Okay, so definite integral. Okay, according to the definition, you have to divide. This is a function. Okay, we assume the function is smooth. Okay, it's from A to B. First of all, you partition the interval. It's not necessarily the same size. A equals A0, x1, all the way to xn and B. That's an arbitrary partition. Then in each interval, I take a point, subinterval. I take an arbitrary point. Okay, so put it this way. This is a xi star, an arbitrary point. Okay, then I look at the value of this. I consider the product f of xi star times the size of delta xi. Now this is the size delta xi, which is xi minus 1. Okay, the size. So if the function is positive, the geometric meaning of this product is the area of that piece. Okay, then you add them together. Okay, you add them together, you will get, so-called the Riemann sum. I from 1 to n, f of xi star delta xi. Okay, that's called a Riemann sum. The Riemann sum, if function is positive, and the Riemann sum is just the total area of this rectangles. Okay, this rectangle is put together is going to be a good approximation of the region under the graph. Okay, so the geometric meaning of this Riemann sum. Okay, if f of x is positive, okay, then the Riemann sum is a good approximation of the area under the graph y equals f of x. Okay, because the region is covered by those rectangles. Okay, this idea actually many people have, even haven't have studied calculus. Why? Well, assume this region. This looks like a backyard. Okay, it's very natural, right? It's not always a square rectangle type of backyard. Then how do you measure the size of your backyard, right? What is the area of that, right? How do you do that, right? Because maybe this is a kind of brooks, so behind that's not your territory. So the idea is that along the source side house, every 1 meter, okay, 1 yard or whatever, will meet. You choose a point, and you measure the length from the source to the north side, okay? And this changes, right? Yeah. Then you find the area of each rectangle you got. Then add them together. This is a very good approximation of the area of the backyard, okay? And the more accuracy you get, and the more points you choose along the source side. Okay, the source side is a strict line, right? That's the way how to do that. You cannot say, "Oh, I assume this is a trapezoid," and just measure, and then it's not accurate. That's a bigger, yeah, because it's curved on the north side. Okay, so this is a yeah, this is the idea many people have. So we use this idea, right? Then, in order to get the precise area of that region, what do? Take a limit, right? You make the subinterval size smaller and smaller and smaller, okay? So the value of this integral should be equal to the limit and those Riemann sum. Okay, it's harder to talk about the limit. It's not like a sequence of numbers, and everything changed. Even the size of the interval. So it's delta xi, all of them should be go to 0. Okay, so I should say the maximum value of all this the length of the subintervals. Okay, I don't care where the point xi stop. Anyway, it's in the subintervals. So if this limit exists, then we say the function is integrable. So f is integrable if the limit exists. Okay. Okay. I'm not going to go to details how to define the limit of such complicated Riemann sums. Okay. And it's not only just a function of n. It depends on n, it depends on xi star, and it depends on delta xi. Lots of them. But we want to make sure the partition of the interval, the subinterval, the length, they're all uniformly approach 0. Then if you get a limit, and that should be the definite integral. Okay, and this, when the function is positive, then this is a if f is greater than 0, then this is going to be the area, should be the area of the region under y equals f of x squared. Okay, so this is the idea we use to find the area of a circle or f semicircle. Okay, because we as human beings, we define the area only for the rectangles. All the other type of regions, we have to find a way to approximate the area, okay, using the limit. So the limit idea, it's already we have long time ago, okay. So this is a definition, okay. All right, now questions. If you know the definition, you know how to estimate the definite integral, because the integral, definite integral is the limit, right? So we can use estimate, right? So the integral of the function is definite because it's a limit. So as long as you choose, okay, as long as you choose a partition of the interval and the points in each interval, you get a Riemann sum. This Riemann sum is going to be a good approximation when n is sufficient large and the size of the subinterval is going to be small and small. Okay. Now we are going to look at some special choices of partition for the interval. So look at the first case. Okay, we called left and right end. Yeah, let's look at right end point approximation. Okay, the idea is that this is the interval, right? A and B. Okay, I'm going to choose subintervals equal size. So that means delta x is going to be b minus a over n. I don't want to take an arbitrary partition. Okay, then x1, x0 is still a, x1 is going to be a plus delta x, x2 is a plus 2 delta x, and keep it going, and xi is going to be a plus I delta x, okay? And xn is a plus n delta x, which is b. Yeah. All right, so this is a special partition. And then xi star is not an arbitrary point. We are going to use a right end point, which is xi. This is called right end point. This is the right end point of this interval, because we do have, this interval, right? Xi minus 1 xi. Okay. Then the Riemann sum, then the integral of this function is going to be approximated by this special Riemann sum. Here's xi, and then delta x, because all the delta xi is the same as delta x. Right? Yeah. Right. Similarly, you can get right end point, right? Left end point. I'm not going to talk about left end. And let's take a look at. We can do the comparison later. Okay, let's look at some approximation. So some people may be thinking, okay, we should choose a point in the middle instead of the end point. Maybe we can get a better approximation. In some cases, yes, because look at this, right? Here, x minus 1 xi. Now, if we choose the right end point, the product, it looks like this part, right? And if you choose the left end point, you end up with this part. So one is too small, the one is too large. So the estimate, So if there is, if you choose, second part is the left end point as approximation. I'm not going to draw the picture again. I use this about left end point approximation. Okay, xi star is going to be xi minus 1. So in that case, and for that function, clearly the left end point estimation is smaller than the right end point approximation. Okay, so make simple observation. So if the function is increasing, and clearly f of xi is larger than f of xi minus 1. Okay, so here's a note. If f of x is increasing, let me draw it. Then the left end approximation is smaller than the limit in the middle. And smaller than the right and approximation. Okay. So how do you do that? Some people maybe will do the following way. Just maybe take the average value. Okay. If you take average value, then you get better estimate. Okay. Right. Add them together. If you add those two together, the mean value of these two should we get better estimate, right? One number is smaller than one number is larger. So conclusion is in this particular case, I can add them together. Right? A better estimate. Okay, this will be a better estimate. Yeah, but this estimate is called trapezoid estimate. Why? Because this sum, when add them together, take the average value, is going to be, look at the picture here, right? Here's x minus 1, here's xi, right? So this plus this, okay, multiply by that. It's actually the area of this trapezoid, right? It's the area of the trapezoid. So how do you remember the area formula of a trapezoid? So top base plus the bottom base divided by 2 and divided by the height. Height here is delta x. Okay, so this is a trapezoid. Okay, then we can call it trapezoid approximation. So we use a trapezoid instead of rectangle to estimate the area and the graph. Right? Yeah, how to get trapezoid? And at the very beginning, we did not realize that. We just added those two estimates, left end point estimate, right end point estimate. And we find out its natural idea to add them together divided by 2 should be a better number, better estimate for the integral. All right, then we combine them, we find out the term in the middle. This product actually is the area of the trapezoid. So then it's called the trapezoid approximation. Now you can also, some students say, why not I choose a middle point? If I choose a middle point, and this is called the xi bar, which is xi minus 1 plus xi. This is a middle point. If the middle point, you can also claim that this can be estimate, get a better estimate in some way. Okay. See, there's a slight difference here. What the picture shows that if the graph is a strict line, there's no difference. So this is an x-axis, y-axis. Okay, let me draw the picture. Here x minus 1, here xi, here's a mixed point xi bar. So the product actually is the area of this rectangle. And there's two parts. One is a triangle on the top. You know, not exact triangle. If this is a curve is a straight line, then it's the same. Okay. If the curve is not straight line, there's still a small error there. Okay. So this should be also better approximation than the left hand point approximation or the right hand point approximation. We call it the middle point approximation. Right? So my opinion is that the middle point approximation or the trapezoid approximation in general should be better than the left end approximation or the right end approximation. Okay. Okay, so let's take a look at some examples, and we are going to see we're going to compare. Okay. So the earlier days, people don't have a computer, but they are 100 years ago, right? That's not too long ago. And there, how do you estimate, right? The integral. So this is where they're doing. Okay, and we know how to define the natural log 2. Like this, right? We know this is going to be natural log x, and that's natural log 2. But what is the exact value of natural? Oh, what is the approximation? Right? This is the area of the region. Okay, this is going to be the area under the graph. Okay, and the x is between 1 and 2. So if you draw the graph, it looks like that. And here's a 1. Here's a 2. So that is the area. Okay. Yeah, this is a graph. Y equals 1 of x. Okay. Now, yeah, 100 years ago, there was no computers, right? I still remember the first time I used a calculator. Okay, you probably don't remember that. Yeah, I think when I was in high school, first calculator. Yeah. All right. So so we want to find a way to estimate. There's no way to get the exact value for natural log of 2. So the idea is, yeah, estimate. Suppose this is a region, right? You can draw a straight line between 2 endpoints, so you get a trapezoid. You say, "Oh, the area of my backyard just like about the area of the trapezoid." That's fine. Okay, but it's curved. They have to minus a small piece. Okay, if we connect those 2 points, right? You do get a trapezoid, then it's curved, so there's a part missing here. Okay, so let's try different substitutions. So we divide the interval into 4 parts. So n we set to 4, otherwise too complicated. Computer can do the computation nowadays even n equals 1 million. Okay, and then it's really very accurate. Okay, it's amazing. Yeah. Quantum computing will be much faster. I'm not sure they are already quantum computing. There was a research institute in Santa Barbara, okay, by Microsoft. I visited that institute. They hire many people working on the quantum computing. Yeah, that will be a big jump if they succeed. Okay, so here delta x, you divide the whole interval by 4, that's quarter. Okay, then x is going to be 1 plus I delta x. It's 1 plus I over 4. Okay, so I is stand for 1, 2, 3, 4. When it's 4, it's just 2. Okay, yeah, and then I'll start at 0. 0 is just 1. 1, 2. Okay, so let's look at the left end. Let's look at the left end point as approximation. Okay, no space. Yeah, left end approximation is n equals 4. I start from 1. F and x minus 1 delta x, because you use left-hand point. Okay. Now, if you write down the details, which is going to be, okay, f is just 1 of x. So I start from 1 here, right? And then even put more details. You have to I minus 1 is going to be 1 plus here I minus 1 over 4, right? And delta x is 4. Okay. Yeah. And you can simplify a little bit. You can simplify 4 canceled out. I think I will 4 plus I, so I plus 3. Yeah, after you simplify. 4 canceled out, the 4 plus I minus 1. Okay, so I start from 1. It's going to be 1/4 and 1/5. When I equals 3, 1/6. When I equals 4, 1/7. So this should be the end estimate of the integral. This should be the end estimate of the integral. Okay, and you can combine them, get a fraction. Okay, you can get a fraction. So this will be the end estimate. If you look at the graph, you see, this is will be, if you use the left end point, then this will be the overestimate. Okay, because the graph is decreasing. Yeah, it's overestimate. This should be larger than the integral from 1 to 2 1 of x dx, which is natural log of 2. So natural log of 2, yeah. Now, if you use right end point approximation, you can quickly see that right end point approximation will be smaller. Okay, so let's look at, okay. So you put the details there. This will be 1 over xi delta x. Then let's continue. Xi is going to be 1 plus I over 4 times 1/4. Then we simplify it. So this time is going to be I plus 4. Okay. So if you put all the details, when I equals 1 is 1 over 5, 1 over 6, 1 over 7, and 1 over 8. So clearly, this is an estimate smaller than natural log of 2. Okay. Because it's underestimate. I think, let me rewrite it, okay? 1 over 5, 1 over 6, 1 over 7, plus 1h, less than natural log of 2, less than, okay? That is interesting inequality. Yeah. Of course, the number on the left side is smaller than the number on the right hand side, right? Yes. 5, 6, 7 here. 1 over 5, 1 over 6, that's the same. But the 1 over 8 is definitely smaller than 1 over 4. So natural log is between there. Okay. So let's write down all the possible estimates. So for this one, I'm pretty sure I can have an inequality. Then let's look at the middle point. Middle point approximation. Middle point approximation. You see, remember, xi equals 1 plus I over 4, right? So the middle point is going to be half of xi minus 1 plus xi. Okay, let's figure out the formula. Okay. 1 plus 4 here, I minus 1, plus 1 plus I over 4. Okay. So it's a little bit complicated, right? It's actually it's going to be 4. Here's 8. Add them together, and here's 2i minus 1. Yeah, I can write as 2i plus 7 divided by 8. Okay, so that's the middle point for me after you simplify. Okay, so now okay, so that would be again it is going to be 1 over xi bar delta x, and I can get turn upside down, okay, a quarter. Okay, so let's simplify a little bit. The numerator is 2i plus 7. Then let's write down all the terms. 2, it's 9, 2 over 9. 2, that's 11. 2 over 13, 2 over 14. Now, this is indeed a number. It's actually a good approximation to natural log of 2, but I cannot tell if this is larger than natural log of 2 or smaller than natural log of 2. Yeah, but I'm pretty sure it's between these two, between the above two numbers. We got one number is from left end point approximation. The other one is right end point approximation. Okay, one more. Right, the trapezoid one. We can use a calculator to estimate this. You can see which one is better. Trapezoid approximation. I want you to, yeah, for the problem on the quiz on the test, maybe it's not a bigger problem, but I want you to write down all the terms. Yeah, you don't need to estimate it. Yeah, 250. You're right. Okay. Okay, it's increased by 2 each time. Hey, trapezoid approximation. Right, trapezoid approximation, by definition, it's going to be half of f of xi minus 1 plus f of xi. Just add them together, right? So I needed to figure out this two. Okay. So it's a little bit difficult to do calculation. This is 4i from 1. Here's 2, 1 over xi minus 1 plus 1 over xi. And this will be just delta x. And let's put the details. Xi minus 1, right? Remember, it's 1 plus I minus 1 over 4. Whoa, it's 1 plus I over 4. And then a quarter. Now, if we do that by hand, it's really complicated. The machine can do very quickly. Okay. Now, actually, 100 years ago, this idea that they found out, actually, we use that to write a program for the computer to estimate the integral. Okay. When you use a software, say, evaluate this integral. Sometimes I give you a precise number like a pi or square pi. But in many cases, you have to tell the computer, hey, give me a numeric approximation. Then they definitely will give you answer. Without telling the computer numeric estimate, then sometimes when you click a return, you get nothing. because there's no such number can describe it. The value of the integral is going to be irrational number. Okay, there's so many different irrational numbers. We don't have a name for that. We only have a names for few irrational numbers. Involves pi or e. Okay, so let's multiply this out. It is going to be 1 over, multiply this out is I plus 7, I plus 3, I plus 4. Okay, we still have to add them together. Maybe maybe you can still separate, but if you want to combine them, this will be there are some terms only two endpoints, just single value. If you write down detail, otherwise it's actually just a sum of those two estimates. The average value of those two estimates. One is on the right side, other one is on the left hand side. Then there's overlap part. This is the overlap part, right? Okay, just add them together, divide by 2. That's how do we get the trapezoid estimate? Okay. Yes. Okay, just add them together, divide by 2. So what do we get here is this part, that part, this part remains same. So if I give you the details, this is actually, okay, half of a quarter plus 1 over 8 is the same. Other part will be like that, okay? Yeah, you can get the details. So the part in the middle will be the same. You have a double of 1 over 5, double of 1 over 6, double of 1 over 7. All right, so this should be the best estimate of the so if the function is a decreasing function, or the function, if the function is increasing, then it's clear that the trapezoid estimate or the middle point estimate is better than the left end estimate or the right end point estimate. Okay. Now, if the function is not what's the geometry meaning of the integral? If the function, let's assume that let f of x be continuous. Okay, it's not broken on the interval from a to b, and this is a picture, and sometimes going up and down, right? And this is a, that's a b. Now, the area of that region we call A1. The area of that region we call A2. The area of that region we call A3. So the geometric meaning of this integral is actually is a signed area, we call it signed area. Okay, what does that mean? That means it's A if that region is above the x-axis, minus A2 if the area is below the x-axis, and plus A3. Okay, that's general case. If the function is always above the x-axis, then you only have one region above the x-axis. That's a positive. That is the area. That should be the area of the region. So the integral is just all the combined, we call it net change, all the combined effort, right? Okay. And like your happiness is a function of t, you measure it, right? If between -10 to +10, like every day you write down. Today I'm happy. Okay, rankings from between 0 and 10. You put a 10 or extremely happy or on 5. Every day you write down the number, right? Sometimes it's very bad. It's not happy, -5. But total, the whole year, you have a 365 days, right? And the integral is just add all those numbers together. Okay, and then you look at it. Are you really happy the last year? Average, right? This is where you measure your happiness, okay? Not only daily, it's over a whole period of time. Okay, so this is like a signed, it's a signed area or signed sum, yeah. If the function is a discrete function, then this will be the signed sum of those numbers, could be positive, negative. Okay, and the average value will be just you have to divide the size of interval, like yeah, the average value. The average value, okay, average value is going to be the integral of this function b minus a. Okay. Yeah, we want to know the average value because the function itself as a quantity, it changes every day, right? Yeah, we have to use the numbers to describe it. Like if we visit doctors, it's like how pain you bake, right? Right, from 0 to 10, you have to tell them. You have to choose a number to decide. That's your fear, All right. So this is this is the average value, and could be 0, the average value. Okay, if the area below the axis is the same as the area above the axis. Okay, and that's all. We get some idea about how to approximate the integrals. And if we understand the ideas, we can even write a program for the compute to do the estimate quickly. Okay. This is this is the idea behind the screen when you type the function, and by default, the computer choose like n equal to 100, depends on how accurate the data, the value you want to get. Okay, and if the computer is doing very fast, you can set n to be 1 million, and sometimes you have to wait for the whole night and get up the next day and say, oh, this is the result. Okay, and is this okay? You can also use this computation to check how fast your computer. Okay, I find out when I buy a new computer, I use the same computations for the same problem. I just put there. Last time I spent 10 minutes waiting, then this time only 2 seconds. Oh, this is really fast computer. Otherwise, it's harder to tell if the computer is fast or not. Okay, yeah, this is how do we do the computation. Okay. Yeah, the first computer I bought, I remember it's cost lots of money. I think it's more than $1,000. Only 200 megabytes. 200. It's on a hard disk drive. You can only save a few documents, Microsoft documents. Okay, so let's do the